Welcome back. Today, we're diving into a genuinely monumental explainer, looking at a threshold that has literally just been crossed in the world of cybersecurity. We're unpacking a fascinating new report from Anthropic, and it details how their AI model, specifically the Claude Mythos preview, didn't just write some clever code or, pass a standard test. Instead, it actually discovered fundamentally improved ways to attack complex cryptographic algorithms. We're talking about the underlying math that keeps our entire global digital infrastructure safe. So this is a story about autonomous AI agents, massive computational power, and a massive shift in how we secure our digital future. But before we get into the heavy mechanics, I want you to picture a really stubborn digital detective. When researchers first pointed this advanced AI at one of the world's most secure encryption standards, the AI actually pushed back. It flat out refused to do the work. It gave them a message basically saying, I found nothing because there's nothing easy to find. It legitimately thought the cipher was unhackable. How the human researchers managed to coax this AI out of its refusal and into a massive world-class breakthrough, well, that's the absolute heart of our explainer today. Section 1. AI enters the crypto arena. Okay, let's dive into this and quickly set the stage. To truly appreciate what this AI pulled off, we need to understand exactly what it was up against. At the core of all digital security are cryptographic algorithms. You can think of digital signatures sort of like the world's most rigorous ID check. When you visit a secure website, this math proves the site is actually authentic. Then you have symmetric ciphers. Imagine these as impenetrable steel lockboxes, where both you and the website hold an identical, perfectly matched key to read the data inside. Without these mathematical systems, every email, every single bank transfer, and every private message would be completely exposed. Now, AI has been used in cybersecurity for a while, right? But up until now, it's been almost exclusively to spot human implementation bugs, like finding a misplaced line of code or a library error where a human programmer just used the algorithm incorrectly. But what makes this new research absolutely game-changing is this monumental shift. The AI didn't just find a typo. It actually discovered flaws in the underlying fundamental mathematics of the algorithms themselves. It found a crack in the foundation, not just the paint. Now, before anyone starts panicking about their online banking, I need to explicitly state this upfront. No current production systems are at risk. The discoveries we're looking at today are incredible for research, for sure, but they do not currently affect any deployed production software. So you don't need to go change all your passwords today. The systems attacked here were either early candidates for future use or reduced simplified variants that academics use specifically for stress testing. Section 2. Case 1. Weakening Hawk. And this brilliantly illustrates the difference between the AI's two very different targets today. On one side, we have Hawk. That's a cutting-edge, post-quantum digital signature candidate designed for the future. On the other side, we have AES, which is the traditional, battle-tested symmetric cipher protecting our data right now. We're going to start by looking at exactly how the AI dismantled the futuristic defenses of Hawk. So, Hawk isn't just some random weekend project, it is a heavyweight. It's a third-round candidate in the U.S. government's NIST competition to find new cryptographic systems that can actually survive attacks from future quantum computers. It has a serious pedigree. In fact, it survived 2 full years of intense, expert human review. Its security relies on some incredibly complex math called the lattice isomorphism problem. To put it simply, the brightest human minds in cryptography hammered at this thing for 2 years and concluded it was highly secure. Enter the AI. Using a multi-agent workflow, where different AI personas basically bounced ideas off each other, Claude Mythos Preview discovered a specific, unexploited mathematical symmetry, a blind spot called a non-trivial automorphism. And honestly, the most staggering part? It didn't take years to find. It took just 60 hours of computational work. In less than 3 days, the AI uncovered a mathematical flaw that evaded human experts entirely. And that brings us to a really crucial number, 2. That 60 hours of AI work effectively reduced Hawk's key size by a factor of 2. Now, in the math of cryptography, that is devastating. It means you'd have to double the key size just to maintain the originally intended level of security. And because doubling the key size ruins the efficiency of the algorithm, this single AI discovery makes Hawk largely impractical for its intended real-world use. Section 3, Case 2. Hacking AES. Now, as impressive as that Hawk discovery was, it was really just the prologue. Let's move to our second case, where the AI takes aim at the absolute gold standard of global encryption, the Advanced Encryption Standard, or AES, was adopted back in 2001. It is without a doubt the most scrutinized encryption algorithm on the planet. This is the ultimate impossible case for our digital detective. Now, full AES 128 uses 10 rounds of encryption. Because the full 10 rounds are fiercely secure, academics study reduced round variants to estimate potential future vulnerabilities. In this case, Claude was tested on a 7-round version to push the boundaries of cryptanalysis. And this is where the story gets really dramatic. On day 1, working entirely autonomously, the AI essentially gave up. Remember that quote from earlier? It told the researchers that AES was too hard and nothing could be found. But on day 2, a human researcher intervened. They prompted the AI, actively encouraging it, explicitly telling it to act like a top researcher and look for genuinely novel, hard findings. They basically pushed it past its own programmed hesitation. And by day 3? Oh man, that encouragement paid off massively. The AI autonomously output 1 billion tokens of thought process and discovered an entirely new fingerprinting algorithm that it named the Mobius Bridge. Now, what's really interesting about this slide is the sheer scale of the breakthrough. The Mobius Bridge fundamentally optimizes a technique known as a meet-in-the-middle attack. By developing a fingerprint that bypasses the need to guess certain values, the AI didn't just slightly improve upon decades of human academic research. Depending on the exact measurement, this AI-generated attack is between 200 and 800 times faster than the previous best human methods. Let that sink in. And here is a number that will make both researchers and security professionals sit straight up. $100,000. That was the approximate real-world API cost required for the AI to autonomously develop each of these complex attacks. For the price of a luxury car, this system produced novel, world-class mathematical breakthroughs that fundamentally altered our understanding of these ciphers. Section 4. The Human Verification Bottleneck. Which brings us to a critical, maybe even a little slightly concerning paradigm shift in how academic research and cybersecurity actually function in the age of frontier AI. Just look at this contrast. It took the AI just 1 week to autonomously brainstorm, test, and formalize the massive AES Mobius Bridge discovery. But it took 2 human researchers nearly a month of full-time work just to verify that the AI's complex mathematics were actually correct. The machine is outputting billions of tokens of high-level mathematical reasoning, and the humans simply cannot read and comprehend it fast enough. This completely flips the traditional model on its head. Historically, human experts spent years trying to crack algorithms, struggling to find the math. Now, AI models are autonomously producing the novel research, and the cybersecurity community is struggling to keep up with the validation. Humans are no longer the discoverers. We have actually become the bottleneck for technical verification. It is taking hundreds of hours of human labor just to double-check the AI's homework. Let's move to and see how this builds into an entirely new scientific method. Step 1, the AI is scaffolded to autonomously pose its own mathematical hypotheses. Step 2, it writes the code to run its own experimental validations to prove itself right or wrong. And finally, step 3, the human researchers step in purely to verify the technical findings and prep them for peer review. The actual engine of discovery has fundamentally changed hands. Section 5, the future of security. So what does this all mean for the road ahead? If AI can crack a post-quantum candidate and radically speed up an attack on the world's most scrutinized cipher, where does it go from here? Well, it turns out Claude didn't stop at Hawk and AES. The researchers pointed it at Leah, which is a lightweight cipher used in low-power international standards. The AI dismantled a 13-round variant, recovering the key in under an hour on a standard desktop computer. It also found practical key recoveries for 6 rounds of the Serpent cipher, and it made distinct improvements on attacks against Salsa 20, Poseidon, and SHA-1. The AI is systematically working its way through our cryptographic library. Recognizing the sheer magnitude of this capability, Anthropic definitely isn't keeping this in a silo. They've launched Cryptanalysis Bench, partnering with leading academics at ETH Zurich, Tel Aviv University, and TU Berlin. The goal here is to officially evaluate and track how these large language models evolve in their cryptographic capabilities over time. As these models get smarter and smarter, we absolutely need a rigorous benchmark to measure exactly how good they are at breaking things. But hey, the ultimate takeaway here is actually incredibly positive. The whole point of cryptography is adversarial review. You build a wall, you invite people to try and knock it down, and then you build a stronger wall. AI is now the ultimate stress test. By utilizing AI as an adversarial tool, researchers can discover dormant weaknesses in our global ciphers before they're ever deployed. we can proactively design stronger, vastly more resilient cryptographic schemes to protect the internet. I want to leave you with this final provocative thought. Today, the models are breaking candidate schemes and reduced round variance. It's theoretical, it's academic, and it's safe. But as AI capabilities scale exponentially, we are rapidly approaching a critical horizon. What happens when an autonomous AI, perhaps operating without a human bottleneck to verify its output, discovers a fundamental flaw in a full crypto system with immediate real-world impact? It's a huge question that governments, academia, and industry must answer right now. Thanks so much for joining us on this explainer, and as always, keep questioning the code.